Hello. This video, this video is maybe the worst video, the last video you want to watch from this course. I know this is the just dry, dirty, uh, like boring theories, and I wish I had Blackboard or I see your faces, but nothing can be done. And I remember when I first learned those things, like I was a college student and I took mathematical statistics from statistics department, and the professor at the time, my professor did not explain anything. So that professor, the teaching style is like this: write down everything on Blackboard and wait for students to take note. And like a few minutes later, the professor asked us, "Any questions?" Of course, no one asked any questions. Then he erases the blackboard. That's it. So like he writes down those theorems, assumptions, theorems, assumption, theorem, and then he say he did something. He does something like this. So first theorem is obvious, so I don't need to explain this. The second theorem is too difficult, so you cannot understand this, so I will not explain. So everything is either obvious, so he does not explain, or too difficult, so we cannot understand, so he does not explain. And now I kind of understand why he did that. So nothing much I can say on those theorems. I try my best. This is really, believe me, it's my best, and I believe I'm doing a good job relative to my professors. Um, and but still, it's not. It must be boring and still difficult, counterintuitive, but it's a really difficult topic to teach. And yeah, let's go. The next theorem is continuous mapping theorem. The main question about this here is we are interested in we know the behavior of a sequence xn. We know that xn converges x in probability or in distribution. But we are not interested directly in xn, but a function of x. And the function is nice in that it is continuous. Then our question is, then the continuous function of the xn converges to the natural limit? The answer is yes. Yes, the natural work, it is natural to assume that the limit is also the continuous mapping of the limit. And so obvious. Example, suppose that something converges to something, and then its inverse is also converging to the limit's inverse, as long as the limit is invertible. So later you will see we are going to use this result directly in many derivations. So and in this point, in this example, the point here is the inverse function is a continuous function, which is like 1 over x is continuous as long as x is not 0. So if the limit is not 0, then continuity is not a problem. Example 2, if xn converges to normal distribution, standard normal distribution with mean 0 and variance 1, then its square converges to the chi-square with degree of freedom 1. So this result, the similar result, this kind of result is useful in hypothesis testing. Later, you will see this kind of results in hypothesis testing, and in this case, and later, you may derive its limiting distribution using the delta method, which is coming in a few minutes. And the delta method, but the difference here is the delta method is an approximation, but this continuous mapping theorem is not an approximation. It is true. There is no approximation error. Anyhow, it's obvious. So continuous mapping theorem is intuitive results. I just put a name on that. When you want to argue that it is true, then you claim continuous mapping theorem. And Slotsky theorem, so I will state the results first. Suppose that xn converges to a constant and yn converges in distribution to a random variable. Then if you think about a continuous function of uh, continuous function of xn and yn, and which is continuous only in the limit, then g of xn yn converges in distribution to g c comma y. So it looks pretty similar to continuous mapping theorem. It looks like the Slotsky theorem is two-dimensional, like considering two sequences at the same time with the same continuity. But so the point is not the dimension of like the two sequences. Yeah, that's the point, right? So the point here is you have to have a constant. One of them, you have two sequences, and the point of the Slotsky theorem is that one of the two sequences should converge to a constant, which means this sequence loses its randomness in the limit. It has no randomness in the limit, so we have the result. That is the result of the implication of this theorem. And why does it matter? Let me explain this first. So the point of this here is if xn converges to some random thing, then the problem here is you need to know the covariance between this and this. Say if xn converges to x and yn converges to y, then what is the joint distribution of x and y? You need to know that. You need to know the joint distribution so that the continuous function of both arguments converges to the nice limit, but it is not possible if you do not have the joint distribution. That's the problem. But in this case, if one of them does not have randomness in the limit, then there is no covariance in the limit. Covariance is zero in the limit. So by assuming that one of them loses its randomness, you say you have the nice result. That's the point. Here is an example. Suppose that xn converges to a normal distribution, yn converges to another normal distribution. Then xn plus yn will converge to a normal distribution, but what is the variance of the summation? The answer is this, but this part is unknown. The covariance is not given by these two assumptions. So you cannot have the result. That is the problem. And here let's see some examples. Suppose that xn converges to a constant and yn converges to a normal distribution. Then xn only contributes to the mean because it converges to a constant without any uncertainty. So simply the variance is not affected. When you multiply xn, then the mean is multiplied by the limit constant, and variance is also multiplied by the limit constant squared. And the second example, remember from the continuous mapping theorem, suppose that we have something inverse converges to something inverse, and another thing converges to normal distribution. And then if you multiply those two guys, because the first thing does not have randomness, you can say that their multiplication also nicely converges to a normal distribution of this form. Right? This is matrix, various matrix, and matrix inverse, like matrix transpose. So, anyhow, the point here is you need covariance, but when one of them converges to a constant, you don't need to know the covariance. That's the point of the Slotsky theorem. And let me finish here. The delta method, the Taylor theorem it is not about statistics, but it is about mathematics. So nonlinear function, like most cases, nonlinear functions will be approximated by a linear function using the Taylor theorem, after assuming that the nonlinear function is differentiable. So if the nonlinear function is sufficiently differentiable, then you can approximate to a linear function. So here is the statement. A function from a vector space to real number is differentiable. Suppose that the function is differentiable, then there exists a point x bar which lies between x and x0. So so what we do here is gx minus gx0. The differentiation is the difference is approximated by the difference in x times some slope, average slope. So here, think about x and x0, and g is moving like this. If it is differentiable, you have average slope, which is what you have here. So there must be a certain point which gives the average slope. And you, based on this linear approximation, we are going to use we are going to get a lot of results based on this. And if you apply that to asymptotic theory, then we say this first order asymptotics, because we only consider first order approximation. If you consider the quadratic term, then that's second order or higher order asymptotics is also possible. But in this course, we will stop here. And x bar is called the intermediate value, or intermediate value. And x bar lies between x and x0 means that you can write it this way. And what's important here is if x converges to x0, then x bar also converges to x0. So that's how we are going to use the Taylor theorem. So here is a direct example of the application of Taylor theorem. Suppose that you have an estimator theta hat, and the true parameter is theta 0, and you have this result, which is like a central limit theorem. And you would like to know g theta hat minus g theta hat minus g theta 0. So you are interested in something different. And then how can we study the limiting distribution of this guy? The idea is to expand this function by the Taylor theorem. So using the Taylor theorem, assuming that g is differentiable, you can write that as this. So exactly this is what I did, and the only difference is I multiply square root and here. Otherwise, just x is replaced by theta, and that's the expansion. That's the first step. And second step, by this we know that theta hat converges to theta 0. So theta hat converges to theta 0. Therefore, theta bar here, this guy, so theta hat converges to theta 0. Then anything in between them should converge to theta 0 too. Theta bar lies between theta hat and theta 0, so it also converges to theta 0. So therefore, we have theta bar minus theta 0 is also smaller p1, because this distance is smaller than this distance. Then additionally, if you assume that the derivative is continuous at theta 0, then by the continuous mapping theorem, this guy, so we know that theta bar converges to theta 0, and this is a continuous function of theta bar. Then you can apply the continuous mapping theorem. So by the continuous mapping theorem, this guy converges to derivative of g at theta 0. we are going to denote it as G, large capital G0. And then by the Slutsky theorem, we have this guy converging to a constant and this guy converging to a distribution. Then if you multiply them, which is a continuous function, then you have this result. So in this short proof, we have used all the theorems we learned earlier. So we used Taylor theorem here, and it's obvious. And continuous mapping theorem, Slutsky theorem. What else? And maybe this is coming from the central limit theorem. So all of these guys, all of these theories are playing some role in the proof, and you are going to see something similar in the future in this course. Okay, the next topic is really the worst of the worst. So look forward to that. See you later.